Yeah, so I will be talking about something not really imaging, but more understanding the visual impact of the Stiles-Crawford effect. And this is a work we have been carried out here in Dublin, in Ireland, where I'm heading the Advanced Optical Imaging group. So, as some of you probably know, the Stiles-Crawford effect is really a classical effect of visual objects. It was discovered by Walter Stanley Stiles and Brian Crawford 89 years ago in 1932, published the following year, and essentially describes in Maxwellian view, which means the light is focused at the entrance pupil, how if we move a light ray towards the periphery of the pupil, the effective visibility drops off, as you can see here in the plot from Crawford's own eye shown to the right. So a few years later, in 1937, Stiles and Crawford independently suggested this empirical Stiles-Crawford function, where you have a peak of visibility centered at a certain point, R0 or not, and then you have also a directionality parameter, rho, which tells you basically how quickly this curve drops off in effective visibility as you move out to the periphery of the pupil. So for the fovea, typically a value of around 0.05 per square millimeter is measured. So this Stiles-Crawford function is not really described here, as you can see, analytically, or we don't really have a scientific basis for it. It is really an empirical function at this stage. So what clinical relevance could it have? Well, it is relevant to know where is the peak of visibility, because that relates to how the photoreceptor cones and possibly the rods are pointed towards a common pupil point, and the directionality parameter is important because it tells us really the acceptance angle of these individual or the combination of photoreceptors. But it still raises a couple of questions. For example, what is the wavelength dependence? What is the eccentricity dependence? How does it depend on the actual length of the eye? And finally, how does it depend on illumination? So, or luminance. There is also a related effect discovered by Stiles, actually also in 1937, where as he was compensating the Stiles-Crawford effect of the first kind, he noted this, that when he compensated the brightness of the reference and the test for two different entrance points, this is what you have in the retina. You have a bipartite field, so a left and a right side, and you're comparing the brightness of the left and the right. When you do the perfect match and the test is not entering through the same point in the pupil as the reference, well, then there is a slight change in color or color hue. This is the Stiles-Crawford effect of the second kind, which has really, I would say, escaped detailed understanding, except of maybe it has to do with self-screening. Nevertheless, we could go back just to the original Stiles-Crawford function and write it out a little bit more sophisticated here. So here we have the peak of visibility now expressed as a function of wavelength. This is essentially the lambda curve of the eye. So if we take a cone population, like very few S cones, maybe 30% M cones and 65% L cones, well, then we get the typical V lambda curve of the eye. And then we can multiply this onto the Stiles-Crawford function. So if we plot this into kind of a 2D plot of the visibility versus pupil point and versus wavelength, well, then you can see in one direction as a function of wavelength, we get the spectral sensitivity, of course. And if we plot at a fixed wavelength across it, just changing the radius, well, then we get the Stiles-Crawford function. So what I really tried to do is just to see what happens if we take the derivative of this function at the off-axis point compared to the essentially on-axis point. And the equation gets rather long, you can see it here, but it's really very simple. It's just the derivative of the first Stiles-Crawford effect. Well, if you plot that one out, this is what you get as a function of wavelength and as a function of pupil point. And I plotted here actually data from Stiles' own original study, where you can see here the wavelength dependence of the hue shift at a certain off-axis pupil point. And if you just take this equation and plot it out directly, you can see you obtain essentially the same results. So this one really shows that the Stiles-Crawford effect of the first kind already includes everything you need to know of the Stiles-Crawford effect. The second kind, for example, we have this parabolic dependence on the radius, which you can see here, this R squared dependence. And we have also, for example, at the peak of visibility, where this derivative here is 0, we have essentially no hue shift, which is happening right in the middle of the, or at the peak of the V lambda curve, 550 nanometer. Now, how do we measure this Stiles-Crawford effect of the first and second kind? Well, together with Ben Lochocki some years back, we set up this system where we have 2 arms. So we use liquid crystals to tune the spectrum and the illumination wavelength, and also the hue separately in the other arm. So we have the test and reference in Maxwellian view, and really do just this brightness match and color match of these 2 half circles, allowing us to take detailed recordings of the Stiles-Crawford effects. More recently, together with Alexander Carmichael, and this is what's part of a European project on myopia, we set up a more sophisticated uniaxial system. And why do we want to have it uniaxial? Well, that's because even though we're using nearly the same components in the 2 branches here, having everything going through exactly the same optics, we can eliminate any kind of artifacts caused by the system itself. So what happens here is, with the digital micromirror, it has micromirrors that can flicker on and off really fast, up to 22.7 kilohertz. And we project images point by point, scanning across the pupil. So this is our test beam, and also we have the reference projected sequentially. So we see a flicker, a really fast flicker, and we adjust the brightness just by changing the duty cycle of the flicker within these 22 kilohertz. So this allowed us to take very nice measurements of how the directionality parameter depends on wavelength, for example, or how it depends on retinal eccentricity in the fovea and going out towards the periphery. We have also looked at myopia, as I mentioned. So once the eye is longer, we get a reduced directionality. This is what you see here in the plot to the right. And this reduced directionality, you can think about it really as the cones just being moved further away from the entrance pupil. So across the normal dilated, maybe 8 millimeter pupil, we get closer to a flat response, simply because of the further separation of the cones from the pupil. So this also follows approximately this very simple linear relationship of how the reduced directionality goes for myopes. Now, the common consensus is that photoreceptors are waveguides, and this is actually work coming out of Rochester many years ago now by Brian O'Brien, suggesting that we have total internal reflection of light in the inner segment, and then possible leakage in the ellipsoid before the light reaches the outer segments, and that of course would give less light in the outer segment. Jay Enoch, some years later in St. Louis, suggested actually an electromagnetic waveguide, and that was developed at the same time as you had optical fibers and telecommunications being developed. So here, it's really a match between how well you couple the light into the inner segment, and then you have radiation, you have leakage, and then you have less light in the outer segment. But for those of you who know me, you also know that I'm still not happy with the waveguide understanding of photoreceptors, because it still leaves a lot of unanswered questions, like what happens to the non-guided light? Why are cones directional at the fovea, whereas the rods are not? They are cylindrical, essentially cylindrical at the fovea, but they're directional, the rods are not. This is, the waveguide light is also transmitted light, it's not the absorbed light that triggers vision. And even how can a single waveguide picture be valid for densely packed and actually quite irregular photoreceptors? Finally, is it the angle of the rays coming in, or is it the angle of the wave vector of the electromagnetic fields that matters the most? So in order to kind of answer these questions, I think of the outer segments more like optical antennas. So if you were an individual visual pigment, how would you like to be situated in the outer segment to capture the light? It's really like a stack of pancakes where you have pigments basically embedded in each layer. You have roughly 1,000 of these pancake layers. And if we know how these layers scatter the light, we also know how they would receive the light and how we perceive the light. This is using optical reciprocity. So it really builds on ideas that were put forward already back in 1948 by Toraldo de Francia in this letter to the editor, published in JOSA A. So going on with that idea, the options are located essentially in a square grid across each disk or each membrane in vagination, and we stack roughly 1,000 layers of these on top of each other. But each layer you could consider it essentially as a mirror. And if again we use the idea of optical reciprocity, the light reflected off a micron-sized mirror is the same as the light going through a micron-sized hole with the diameter of the individual cones. So this aperture is essentially a scaled-down version of the pupil of the eye. So what we need to do now is take all of these layers and keep track of the phase as we go through the outer segment. And this is what we have done here in this paper published now already 7 years ago. And we get actually very similar directionality values to those you observe in psychophysics. So we get rho from 0.05 to 0.1 square millimeter, which corresponds to including a few or all of the band gate layers. That means also we have now a physical basis because a hole, the diffraction from a hole is an Airy disk. So essentially the Airy disk should maybe be a new Stiles-Crawford function. And if you look at it here, plotted together with the traditional, in the red is the traditional one, the Bessel function is the green, you can see we obtain essentially the same visibility curve as the Gaussian function, but we have now a more sound physical basis. If we look at how light is scattered, because the model also gives us what is scattered, well, then we can look at the light, for example, going through the outer segments. It's showing here in a cross section, and you can actually see as it propagates, we have more and more leakage going down the outer segments, and that means we have another explanation for the Stiles-Crawford effect as being light that leaks out of the individual photoreceptors, and there is therefore less light available to capture within the outer segments. If we look at light in the cross-section of the retina, well then here the white dot indicates the diameter of an individual cone, and you get a dark ring very similar to what you actually obtain in high-resolution adaptive optics retinal. But let's return to the basics. Can we add the Stiles-Crawford effect point by point? Remember, it's obtained with Maxwellian light, but in normal vision, we don't have Maxwellian light. We have Newtonian view, so we're using our full eye pupil. Can we just take the mathematical integral? That would be the easiest and most pleasant to do. But it turns out actually that this approach doesn't work, and the results are false. So let me just briefly go through this before I come to the end. So if we look at an outer segment, we have an exponential decay because we have an absorption cross-section of each individual pigment. So we get less light through. In a linear approximation, you could say that the longer the outer segment is, that's the z-axis, the longer it is, the more light we absorb. If we go into 3 dimensions, that becomes a volumetric absorption model, which we published a few years back in Journal of Vision. So what happens for the oblique light? Well, then the overlap or intersection volume is smaller. So this is highlighted here. And we can try to look at it also in this kind of picture. So here we have a foveal, basically a hexagonal packing of the outer segments. And if we come with a very narrow pencil of light, but all collimated onto just the central cone here, we get a very high directionality if we start to change the angle of incidence. But as soon as we start to expand the beam a little bit, maybe to the half the separation here between the outer segments, well, then we get this kind of purple curve that starts to become flat at the top. And the wider we make it, the smaller the directionality becomes. So here you have a possible reason for why the rods are not directional, because the rods are surrounded by rods of exactly the same type, the same rhodopsin molecules in the outer segments. And therefore, even if it leaks, the response becomes flat. So how can we actually try to measure this effect directly? Well, we tried to set up this instrument where we had a motorized iris flickering in pupil size. So we used a 1.4 millimeter reference. We flickered in consecutively larger and larger diameters from 2.5 going all the way up to 7.4. So we're dilated, of course. And subjects are looking onto this back illuminated E here just to keep their gaze fixed. We can change the color and so on and so forth. What they do is they tune the transmission of this liquid crystal tunable ND filter to match the brightness of the small target with the large one. So they would be doing this kind of flicker until they are happy with the match. Then they move on to a larger diameter and so on and so forth. So completing this measurement, you have the points dotted here for different frequencies. In this case, it was in my own eye. And there you see basically the 1/x type of dependence for the volumetric integration curves, following quite closely to the dots. And if we had just done the normal Gaussian-Stiles-Crawford integration, we would have obtained the orange curve. So what can we learn from this? Well, we can learn that the volumetric integration and the actual normal vision compared to Maxwellian light gives a much stronger truncation than predicted by the Gaussian-Stiles-Crawford effect. It's nearly like an order of magnitude stronger the cutoff, and it actually doesn't make a good fit to a Gaussian. So at that point, I just want to thank you for your attention, and I'm open here for questions, and thank you to the team also who have really been involved with all of this work. Thank you.
Thank you, Brian. So if you can keep that slides up so that I can ask some questions. I have one question. As you briefly mentioned toward the end, we always use entire pupillary area to see it, to have a visual experience. How does the aberration or optical quality of the eye affect this Stiles-Crawford effect in terms of cause of Stiles-Crawford effect, or any modification of the Stiles-Crawford effect over the long period of time?
Yeah, so as long as we are with the small pupil, and that's what we have with this strong truncation, right, then the aberrations matter actually very little across a 2 to 3 millimeter pupil. But right, of course, as we get larger with the pupil, the aberrations produce other angles of incidence. They right, modify already the kind of truncation that we have. So there would still be some kind of filtering effect in that sense, that it would leak out of the photoreceptors, I believe. But of course, it's very challenging to check this experimentally at the fovea because of the very small size and packing of the photoreceptors.
Okay.